Somewhere in the Arizona desert, behind a wall of concrete and filtered air, engineers just broke the oldest rule in chip making. And they broke it on purpose. For 60 years, this industry has followed one law. When you build a new manufacturing process, you change one big thing at a time. One innovation per generation, never two. Because if it fails, you have to be able to find out what killed it. Intel changed too, in the same node, in a brand new factory, on the product line that decides whether the company that invented the modern microprocessor still gets to manufacture anything at all. And right now, chips built on that process are shipping into laptops you can actually buy, which means the experiment is over and the results are in. So let me break down what really changed inside this chip, the new transistor, and the far more radical thing they did underneath it. Why the number on the box, 18A, is basically marketing, and why for 1 week in December, a single phone call almost ended this entire story. Subscribe to the channel and let me explain. Before we talk about the chip, we have to talk about where it's being born, because in semiconductors, those two things are the same thing. Right now, a strange race is unfolding in the Ocotillo Desert outside Chandler, Arizona. Not a race between products, a race between buildings. Here stand the two most ambitious chip factories ever attempted on American soil. Intel's Fab 52 and just down the road, TSMC's Fab 21. Two companies, one desert, and two completely opposite manufacturing philosophies. TSMC is copying a process it already mastered somewhere else. Intel is inventing one from scratch, and that difference is the entire story. Start with the scale because the numbers are hard to hold in your head. Fab 52 provides more than 2.9 million square feet of total space. Building it took 4 years and over $20 billion, and it sits inside an Ocotillo campus where Intel's expansion adds up to roughly 32 billion. But square feet don't really tell you anything. Try this instead. To lay the foundation, crews moved over 1 million cubic meters of earth and rock. They poured around 600,000 cubic meters of concrete and set roughly 75,000 tons of steel. That is so much concrete that Intel had to build its own mixing plant on site because local suppliers physically could not keep up with the pour schedule. And none of that concrete was for walls or offices, it was for the floor, which sounds absurd until you understand what stands on that floor. Semiconductor tools operate at atomic precision. Picture an astronaut on the moon aiming a laser pointer at your fingertip here on Earth and holding it steady. That's the alignment budget these machines work inside. A truck passing on a nearby road, a train 2 miles away, the building settling by a fraction of a millimeter, any of it can wreck a wafer. So the entire structure sits on an ultra-rigid base engineered to absorb vibration and isolate the tools from the outside world. And even pouring that base was a fight because in Arizona heat, concrete cures too fast and cracks. So the most critical pours had to happen at night. Before this factory could make a single chip, it first had to survive the desert. Only then does the real building begin, because everything I just described exists to protect one room. In semiconductor manufacturing, cleanliness isn't a policy, it's physics. The transistors being built inside Fab 52 have features only a handful of atoms across. At that scale, a speck of dust isn't dirt. For a modern chip, one invisible particle landing on the wrong spot is the equivalent of a comet hitting a city. One grain, one chip destroyed. And often, not just one chip. One particle can wipe out thousands of transistors and take a whole die with it. That's why every fab on Earth is built around the clean room, and in Fab 52, the clean room is enormous. Roughly 685,000 square feet of tightly controlled space, sealed off from a desert that is actively trying to get inside. And that's the part that should not work. Outside these walls, haboobs roll across the valley, walls of dust that swallow the horizon and fill the air with billions of particles. Inside, the particle count in the air stays close to zero. To hold that line, the air is never still. Massive fan decks push filtered air down from the ceiling in a slow, uniform sheet. It glides across the machines, past the wafers, and vanishes. Through perforated floors. On the way, it passes through ULPA filters that capture 99.9995% of microscopic particles, and the entire volume of air in the room gets replaced again and again, hundreds of times every hour. The result is a room roughly 1,000 times cleaner than a hospital operating theater. But here's the twist. The desert isn't the main enemy. You are. A single human being sheds thousands of microscopic skin particles every minute just by existing. Breathing, walking, turning your head, all of it releases contamination. That's why engineers wear the full bunny suit. Hair sealed, skin sealed, breath isolated from the room. And even then, human presence is minimized as aggressively as possible. Most wafers in Fab 52 never travel with a person at all. They move inside sealed overhead transport systems, gliding silently from tool to tool, spending as little time in open air as the process allows. So you have a building that eats vibration, a room that eats dust, and a workforce dressed like it's going to orbit. All of it for one purpose: to run thousands of process steps, deposition, lithography, etch, clean, then clean again, without a single one going wrong. And that word, clean, brings us straight into the next problem, and it's a brutal one in this location: water. Because cleaning a wafer takes water, an absurd amount of it. Ultra pure water, stripped of minerals, ions, bacteria, dissolved gases. Water so aggressively purified that it's actually corrosive and undrinkable. An average advanced fab can consume up to 10 million gallons of ultra pure water per day, which is roughly the daily use of tens of thousands of homes. And making it is lossy. It takes something like 1,400 to 1,600 gallons of municipal water to produce 1,000 gallons of ultra-pure water. Now put that demand in the middle of a desert in a state where every gallon is already politically contested. So Intel didn't just build a fab, it built a water plant next to it. The Ocotillo brine reduction facility can treat and return up to 9 million gallons of water per day back into the production cycle. That's the trick that makes this location survivable. Not finding more water, but using the same water over and over. And the reason purity matters as much as volume is that a microscopic chemical impurity doesn't just spoil a rinse. It contaminates a batch, which means every membrane, every pump, every filter and sensor in that water plant is effectively part of the chip manufacturing process itself. Without it, a leading-edge fab in the Sonoran Desert simply could not exist. Only after all of that, the foundation, the air, the water, do the machines arrive. And this is where Fab 52 gets its first genuine advantage. Inside are the most advanced production machines humanity has ever built. Extreme ultraviolet lithography scanners from ASML, the systems that print nanoscopic patterns into silicon using light with a wavelength of just 13.5 nanometers. Each one costs on the order of a couple $100 million, and a leading-edge fab needs many of them. But lithography is only the headline act. Around it sit hundreds of other tools that matter just as much. Atomic layer deposition systems that grow films one atomic layer at a time. Plasma etchers that carve those layers into transistor structures. Metrology tools that measure features you cannot see with light at all. Every one of them has to behave identically, wafer after wafer for years. And it's worth pausing on how EUV light is even made, because it tells you what kind of industry this is. You can't generate 13.5 nanometer light with a lamp. So inside the machine, molten tin is fired out as microscopic droplets, tens of thousands of times per second. Each droplet gets hit twice by a high-power laser, once to flatten it into a pancake, once to vaporize it into a plasma hotter than the surface of the sun. That plasma emits the extreme ultraviolet light, and then the problem gets worse because EUV is absorbed by everything, including air and including glass. So there are no lenses. The entire optical path runs in vacuum, bouncing off mirrors so precisely polished that if you scaled one up to the size of Germany, the largest bump on it would be under a millimeter. That is the machine that prints every advanced chip you own, and only one company on Earth knows how to build it. And then there's the machine that makes this factory different from every other factory on the planet. Intel became the industry's first mover on High-NA EUV, the next generation of lithography, and the most advanced machine that currently exists. One system costs about $380 million. It weighs more than 150 metric tons. It ships in over 250 crates, packed into 43 freight containers, moved by multiple cargo planes and around 20 trucks, and then assembled on site over months. What you get for that is optics with a numerical aperture of 0.55 instead of 0.33. And that single change lets the tool print features up to 1.7 times smaller than existing EUV systems, enabling up to 2.9 times more density on the die. That is a real physical lead, and here's how real. TSMC has said that none of its nodes through 2029 require High-NA EUV at all. Intel is building its future around it, which means for the next several years, in one building in Arizona, Intel holds a capability its biggest competitor has deliberately chosen not to buy yet. Whether that's courage or an expensive mistake is exactly what this whole story is about. Because a factory this extreme only makes sense if there's something extreme to build inside it. And there is. Intel calls it 18A. Now, the A stands for angstrom. An angstrom is roughly the diameter of a single atom, and 10 angstroms make 1 nanometer. So 18A, by its name, suggests 18 angstroms, 1.8 nanometers. And here comes the small disappointment, because that number is not a measurement of anything. It used to be. In early semiconductors, the node name roughly matched the physical gate length of the transistor. It was a real dimension you could go and measure with a microscope. That stopped being true years ago. Today, every company measures and names its nodes differently, and the number on the marketing slide is a label, not a ruler. Nothing inside an 18A transistor is 1.8 nanometers wide. So if the number is theater, what actually matters? Two things. Transistor density, how many devices you can physically pack into a square millimeter, and drive current, how much current a transistor can push the instant it switches on. Think of drive current like water pressure in a pipe. The stronger the flow, the faster the next stage of the circuit can flip. More drive current means faster switching, which means higher clocks at the same voltage or the same clocks at lower power. That's the real currency, not the name. By those measures, Intel's own claim for 18A is up to 15% better performance per watt and 30% improved density compared to Intel 3, which is a solid generational step. But it's not the interesting part, and it's not why this node is dangerous. The interesting part is how they got there, because they didn't take one step. They took two at the same time, and the industry does not do that. The first change is the transistor itself. Strip away everything else, and a transistor is a switch. It turns a current on and off billions of times a second, and every calculation your device performs is built out of that one action. For more than a decade, the entire industry ran on one design: FinFET. The channel, the path the current flows through, gets lifted up into a thin vertical fin, and the gate wraps over it on three sides so it can squeeze the current on and off. FinFET carried us from early smartphones to the GPU's training frontier AI models. It was one of the great inventions in this field. But physics always catches up. To keep scaling, the fins had to get thinner and thinner and taller and taller. Imagine a wall 6 nanometers thick and 10 times that tall, built billions of times over with atomic consistency. Eventually, the gate loses grip on the channel. Electrons start leaking through when the switch is supposed to be off. Leakage rises, control drops, and the transistor stops getting better no matter how much smaller you make it. FinFET didn't fail, it just stopped scaling, and when a device stops scaling, you don't optimize it, you replace it. The replacement is now running inside Fab 52. Intel calls it RibbonFET, and the industry calls the general architecture gate all around. Instead of one tall vertical fin, the channel becomes a stack of extremely thin horizontal sheets of silicon, ribbons laid one above the other. And the gate no longer wraps three sides. It wraps all four, completely surrounding each ribbon. That's the whole idea. And it's why it works. More gate surface touching the channel means far better electrostatic control, which means less leakage, better drive current, and room to keep shrinking. It also gives designers a new dial, because you can tune the width of the ribbons to trade performance against power on the same chip. So RibbonFET keeps the scaling curve alive, and every serious foundry is going the same direction. TSMC's N2 uses gate-all-around. Samsung's SF2 uses gate-all-around. On its own, this is not a revolution. It's the industry's shared next move. The revolution is what Intel did underneath, because there's something in a microchip that has barely changed since the integrated circuit was invented, and almost nobody outside the industry ever thinks about it. Not the transistors, the wiring, and specifically how power gets to the transistors in the first place. For 60 years, every chip on Earth followed the same blueprint. Build the transistors on the surface of the silicon, then stack everything else on top of them, layer after layer of metal, sometimes 15 or 20 layers, all of it above the devices. And here's the thing most people miss. That stack contains two completely different kinds of wiring forced to share the same space. Signal wires, which connect billions of transistors into logic, thin, fast, delicate, and power wires, which feed raw current into the chip, thick, noisy, carrying enormous amounts of energy. Two networks with opposite requirements, competing for the same real estate above the same transistors. For decades, that was tolerable. Then transistors kept shrinking, and two problems started to dominate. The first is what chip engineers call IR drop. Push current through a wire and some voltage is lost along the way, and the thinner the wire, the more you lose. So by the time power crawls through that maze of metal and arrives at a transistor, it's weaker than it should be. The transistor still switches, but it switches slower and less predictably. Now multiply that across hundreds of billions of transistors, and you get a chip that has to run at a lower clock or a higher supply voltage just to stay reliable. You're paying for performance you designed and never receive. The second problem is congestion. Think of rush hour. A modern processor has hundreds of billions of transistors, and each one needs to connect to many others, which means an explosion of microscopic wires all trying to route across the same layers. And here's the cruel part. Power lines don't shrink gracefully. They have to stay relatively thick because thin wires can't carry current without melting or dropping voltage. So generation after generation, the power network takes up a larger share of the space that signal routing desperately needs. The more advanced the chip gets, the more the old architecture fights you. The industry managed this for years the way you manage anything you can't fix, with workarounds, more metal layers, smarter routing algorithms, better placement tools, but the fundamental blueprint never changed. Intel changed it. They separated the two networks completely. Signal wiring stays where it always was, on the front of the wafer. Power no longer comes from the top at all. It comes from underneath, from the backside of the silicon, through tiny vertical connections that punch straight up into the transistors from below. Intel calls it PowerVia, and the general technique is backside power delivery. And from a chip design perspective, this is enormous because it fixes both problems at once. Power now takes a short, direct, low-resistance path instead of threading down through 20 layers of metal. Intel's own test silicon showed more than 30% improvement in platform voltage droop and around a 6% frequency benefit purely from the architecture change. Free performance from wiring, not from transistors. And at the same time, ripping the power network out of the front side frees an enormous amount of routing space, which let Intel hit standard cell utilization above 90% across large areas of the die. In plain terms, less wasted silicon, denser logic, faster chips on the same transistors. So if it's that good, and the idea is that obvious, the question writes itself. Why did nobody do this for 60 years? Because building it is brutal. To deliver power from the backside, you have to process both sides of the wafer, and the entire semiconductor industry is built around processing one. Here's roughly what it takes. First, you build the chip normally, transistors on the surface, signal wiring stacked above them. Then you do something that feels wrong. You flip the wafer over and bond it face down to a carrier wafer, because from this point on, the front side is too fragile to handle. Then you grind away almost all of the silicon from the back until only an extremely thin layer remains above the transistors. Then, on that thinned backside, you drill microscopic vertical holes with atomic level alignment accuracy. Land them on structures you can no longer see, fill them with metal, and build a whole second power network down there. Every step of that is a new problem. A thinned, bonded wafer warps differently, conducts heat differently, and cracks more easily. Alignment between the front side transistors and the backside vias has to be near perfect, or the connection lands on nothing. You need new chemistries, new bonding tools, new grinding and polishing recipes, new metrology just to measure whether any of it worked. And this is exactly why we started with the factory instead of the chip. Because at this level, an idea is worthless without a building that can execute it. Moore's Law was never purely about physics. It's about whether the equipment can keep up, which brings us to the gamble. And this is where the story gets genuinely uncomfortable. Intel originally had a safety net. Before 18A, there was supposed to be an intermediate node called 20A, and the plan was textbook. Introduce the new transistor first, take the yield pain, learn the failure modes, and add backside power in the following generation. One variable at a time. Exactly what 60 years of institutional knowledge tells you to do. Intel canceled 20A. And you can see the logic, even if it terrifies you. When you're already behind, every extra generation you spend de-risking is a generation your competitor spends selling. So Intel skipped the learning step and went straight to the node. The company's survival depends on carrying two fundamental changes at once into a factory that had never run a single wafer. The difficulties showed up almost immediately, and they showed up stacked. Lithography alignment issues, deposition and material problems, multiple new failure mechanisms interacting at the same time, which is precisely the scenario process engineers spend their careers avoiding, because when three new things can break, a bad wafer doesn't tell you which one broke it. And then there's the number that decides everything: yield, the percentage of dies on a wafer that actually work. Yield is not a technical detail, it is the entire business. At high yield, a fab prints money because the cost of a wafer is roughly fixed whether you get 400 good chips off it or 40. At low yield, the economics simply collapse. You can still ship product. It just costs you more to make than anyone will pay. That was Intel's position for most of the ramp. The company's own CFO said publicly that 18A yields remained below profitable levels and would not reach the cost targets they wanted until the end of 2026 at the earliest. Read that again. They started high-volume manufacturing on a node that was still losing money per wafer because stopping was not an option. And this is where that December phone call comes in. By late 2025, Intel had done something remarkable on paper. It had convinced NVIDIA to put roughly $5 billion into the company, and it had NVIDIA evaluating Intel's process. Then, in December, reports landed that NVIDIA had halted its testing on 18A. Intel's stock dropped the same day, and the message the market heard was devastating in its simplicity. The most important potential customer in the world looked at this process and walked away from the test. Not because the physics didn't work, because the yields and the economics weren't there yet. That is the moment where a semiconductor moonshot usually dies. Not in the lab, but in a spreadsheet. Except this one didn't. What happened next is the least glamorous and most impressive part of the whole story, because it wasn't a breakthrough, it was grinding. Intel reported yield improvements running at roughly 7% per month, sustained over many months. And in mid-2026, the specific problem that had been poisoning the ramp was reported fixed, wafer-to-wafer variability. That's the ugly failure mode where the process produces good wafers and bad wafers from the same flow. And you can't tell why. It's worse than a low yield, because a consistently low yield you can debug. Random variation means you're chasing ghosts. Once that was under control, the numbers could finally move in a straight line, and production across Intel's Oregon and Arizona sites was reported climbing toward roughly 30,000 wafer starts per month, and the products landed. Panther Lake, Intel's core. Ultra Series 3 reached broad market availability in January 2026, built on 18A with a multi-chiplet design, up to 16 cores, up to 12 XE cores in the integrated GPU, more than 50% faster CPU and graphics performance than the previous generation, and up to 180 platform TOPS of AI acceleration. Then Clearwater Forest, Intel's first 18A server processor, introduced with up to 288 efficiency cores. And an enhanced version of the node 18A-P entered risk production, promising around 9% more performance at the same power, along with a large cut in thermal resistance. And there's a detail in Clearwater Forest that matters more than the core count, because it shows where the whole industry is actually going. That chip isn't one piece of silicon, it's 12 compute chiplets built on 18A, sitting on 3 active base tiles built on Intel 3, alongside 2 I/O tiles built on Intel 7. 3 different process generations from 3 different technologies assembled into one processor. The compute tiles are bonded directly onto the base tiles with Foveros Direct 3D, using copper-to-copper bonding at a 9-micron bump pitch, which effectively fuses 2 pieces of silicon into one electrical structure. The tiles are then stitched sideways with EMIB. Add it up and you get up to 288 cores and up to 576 megabytes of last-level cache in a single socket. Why does that matter? Because a chip like that means the leading-edge node is no longer the whole game. You don't need to build every part of a processor on the most expensive silicon on Earth. You build the logic that benefits from it there, and everything else where it's cheaper, then bond them together. And that is exactly the capability that has become the industry's tightest bottleneck. Advanced packaging capacity is now the constraint deciding how many AI accelerators anyone can ship, which is why TSMC is building packaging plants in Arizona, and why Intel has been pushing its own packaging roadmap hard. Because here's a fact that still surprises people. A chip can be manufactured in America and then flown to Asia to be packaged. The wafer is only half the journey. If you want a real domestic supply chain, you need both halves in the same country, at scale. So the question is no longer whether 18A is real. It's real, it's in products, and you can buy one. The far more interesting signal came in July 2026, and it came from inside Intel. Nova Lake, the next desktop generation, had been planned to lean heavily on TSMC's N2 for its compute tiles, Intel outsourcing its own flagship, which tells you exactly how much confidence there was internally. Then reports emerged that Intel was pulling that work back, with as much as 90% of Nova Lake compute tile volume moving to 18A. That's not a press release. That's a company voting on its own factory with its own most valuable product. And that vote only happens when the yields are real. But solving yield was only the first problem. The second one can't be solved with engineering at all, because Intel doesn't just manufacture chips. It designs and sells them too. And it competes directly with the exact companies it wants as foundry customers. Imagine handing your most valuable design, your entire roadmap, your performance targets to a company that ships a rival product into the same market next quarter. Intel sells Xeon. AMD sells EPYC. That is an extremely awkward conversation to have across a table. TSMC never has that conversation because TSMC doesn't compete with anyone. It designs nothing. That's not an accident. It's the founding principle of the pure play foundry model, and it's worth more than any process advantage because trust compounds. This tension has a name in the industry, the IDM dilemma, and leading edge technology does not dissolve it. Even a genuinely superior process doesn't fix the fact that you're asking a competitor to become dependent on you. For Intel Foundry to win broad adoption, Intel would effectively have to retreat from the product business it currently lives on, which is commercially and politically impossible. So the conflict stays, which makes the exceptions extremely interesting. NVIDIA's roughly $5 billion investment, finalized after regulatory clearance, is not a wholesale shift of manufacturing. The collaboration is focused on joint products and chiplet-level work, not moving flagship GPUs off TSMC. So why do it at all? Because NVIDIA has its own problem. TSMC is full. AI demand has pushed leading-edge capacity into a multi-year backlog, and advanced packaging is an even harder bottleneck than the logic itself. When your supplier is sold out, a second source stops being a nice idea and becomes strategy. Intel's fabs in Arizona and Ohio are one of the very few places on Earth that could ever become that second source. So read it as insurance, not endorsement. NVIDIA gets an option, Intel gets credibility, and the US government, which took roughly a 10% equity stake in Intel in August 2025, converting CHIPS Act and defense funding into ownership, gets domestic capacity for the most strategically important product in the world. And that brings us to the challenge that actually decides this. And it isn't technical, it's volume. A fab this expensive only makes money when it's full. Depreciation doesn't care about demand. If utilization drops, your costs don't drop with it and margins evaporate, which is precisely what happened to Intel the last time it slipped on a node while its fabless competitors stayed asset-light and flexible. So Intel now has to do the hardest thing in this industry: convince companies that have spent 15 years defaulting to TSMC to route real volume somewhere else. And the honest scoreboard right now is mixed. Intel has said it has 2 prospective customers for its next node, 14A, with binding decisions expected in the second half of 2026. And leadership has been explicit that without external foundry commitments, the economics of 14A and everything beyond it come into question. That is the whole company balanced on a small number of signatures. And this is where those High-NA machines come back into the picture, because 14A is the node they were actually bought for. That's Intel's first process designed around High-NA EUV from the start, and it's the reason the company spent $380 million a tool before anyone else would. The bet is straightforward. If you can print a layer in one High-NA exposure that competitors need multiple patterning steps to produce, you cut process steps, cut cycle time, and cut defect opportunities. And defect opportunities are yield. But that bet only pays if there's volume to run through it. Intel has been explicit that 14A's future depends on landing external customers, with mass production targeted toward the end of the decade. So the tool advantage in Arizona is real, and it's also a liability because expensive capability that nobody rents is just expensive. Meanwhile, the competition is not standing still, and the window is measurably narrow. TSMC is running N2 with gate-all-around, and it took the cautious path deliberately. One innovation at a time, protect yield, protect trust. Its backside power node, a 16 with superpower rail, is now targeted for 2027, promising 8 to 10% better performance or 15 to 20% lower power versus N2P. After that, a 14 in 2028 with second generation gate-all-around, and A12 in 2029 for data center. Samsung is on the same journey with SF2 in production, SF2P behind it, and SF2Z bringing backside power delivery in 2027. In other words, the entire industry is converging on the same blueprint Intel shipped first. Gate-all-around plus backside power is not Intel's secret, it's everyone's destination. Intel just got there roughly a year to 2 years early and paid for that head start in yield, canceled nodes, and a very public near-death moment. And Arizona itself shows the difference in philosophy and physical form. TSMC's Fab 21 started with mature 4nm production and has been running it at high yield since late 2024. Its second phase on 3nm began equipment installation in 2026 with volume production pulled forward to 2027. Its most advanced Arizona fab for 2nm class and A16 broke ground in 2025 and is targeted for the end of the decade. TSMC's total commitment in Arizona has expanded to roughly $265 billion across a dozen planned facilities, including the advanced packaging capacity that is currently the single hardest constraint on how many AI accelerators anyone can ship. Eventually, a large share of TSMC's most advanced capacity will sit on American soil. So look at the two buildings again. TSMC brings scale, ecosystem, packaging, and a customer base that trusts it completely. But it deliberately arrives at the newest architecture later. Intel brings the newest architecture first, the only production High-NA EUV tools in the industry, and a factory purpose-built for a process nobody else is running. But it has to prove it can fill that factory with somebody else's chips. And this is why the entire industry is watching a desert in Arizona. Because today, the overwhelming majority of the world's most advanced logic is manufactured by one company, concentrated in one geography, and that is a level of fragility the global economy has never accepted in any other critical input. Every phone, every car, every data center, every weapon system, every AI model traces back through the same handful of buildings. The semiconductor industry was born in the United States. The transistor at Bell Labs, the integrated circuit, Silicon Valley, the entire architecture of modern computing. And then the manufacturing left. That's what 18A is really about, not one company's comeback. If this process holds, if the yields keep climbing, if the customers sign, if the second and third generations arrive on schedule, then the world gains a genuine second source at the leading edge, and the most concentrated supply chain on the planet becomes measurably less fragile. If it doesn't, then the boldest manufacturing bet in decades becomes a very expensive lesson in why you only change one variable at a time. Because here's the uncomfortable truth underneath all of it. Intel didn't reinvent one thing. It reinvented four at once: the transistor, the power delivery architecture, the manufacturing flow, and the factory itself, in a desert that fights you every single day. That's not a node transition, that's a moonshot. And in semiconductors, being first has never been the same thing as winning. Being first means you pay the tuition and everyone else reads your notes. TSMC's backside power node is coming. Samsung's is coming. Both of them will arrive with the advantage of watching exactly what broke in Arizona. So the real question is simple, and nobody can answer it yet. Can Intel turn a 1 to 2 year technical lead into a durable business? Filling that factory, winning designs from companies it competes with, and holding the line through 2 more generations? Or does the industry catch up before the window closes, and Arizona ends up as the place where the hardest process in the world got proven and then got commoditized by everyone who came second? That's what the next 18 months decide. I'd really like to know where you land on this one, so drop your take in the comments below. And if you found this breakdown useful, share it with someone who still thinks the number on the box is the technology. Subscribe to the channel for the next deep dive.